This is Dr. Vermilio. In this lecture, we'll review research studies using the hearing and noise test. There are several terms for speech recognition and noise difficulties in the presence of a normal audiogram. These terms include psychogenic deafness, normal fragile ears, auditory inferiority complex, auditory disability with normal hearing, selective diacusis, obscure auditory dysfunction, auditory diacusis, the King-Kopecky syndrome, named in part after Dr. King from that 1954 paper, idiopathic discriminatory dysfunction, and it has also been called an auditory processing disorder. Here's a question for you. Can we use the hint to measure a hearing and noise deficit for individuals with normal audiograms and the self-report of hearing and noise difficulties? We took a look at 47 native speakers of English. All of them had pure tone thresholds equal to or better than 25 dBHL from 250 through 6,000 Hertz. So all of the subjects had normal audiograms. Then we just asked the subjects, do you ever have difficulty recognizing speech and noise, such as a crowded restaurant or your cousin's wedding? And if they said yes, to some degree that they struggle to hear speech and noise, we put them in the OAD group, or the obscure auditory dysfunction group. So normal audiogram and a complaint that they're struggling to hear speech and noise. That was that group. And then the control group was everybody else, so all with normal audiograms, and they reported that they did not have difficulty recognizing speech and noise. The groups were matched for age composition in order to avoid age effects. The standard hint protocol was used. The composite hint score was determined. And you recall that the composite hint score represents an average of the three hearing and noise test conditions: the noise front condition, noise right, and noise left, where the front condition is weighted, or the front threshold rather, is weighted twice. And then we take those thresholds, take the sum divided by 4, and this score equally weights the noise front and noise side thresholds and provides a single index of overall speech recognition ability in noisy environments. Here are our results for the pure tone thresholds. To make the analysis easier, we looked at the binaural pure tone average. So this is one number to represent the average pure tones thresholds from 500 through 6,000 Hertz, and then it's averaged across ears. So one number to represent the pure tone thresholds across both ears. And you have the control group, no speech recognition and noise complaints. The OAD group reported some speech recognition and noise difficulty. And you see that the two distributions are basically mirror images of each other. And there was no significant difference between pure tone thresholds for these two groups. Now, here are the hearing and noise test results. The y-axis represents the hint composite score in dB signal-to-noise ratio, and a -9 dB signal-to-noise ratio represents very good hearing and noise ability. A -3, as you know, is a more positive score. That represents poor hearing and noise ability. And we looked at the difference between the thresholds for the two groups, and we found that the control group, as you can see, overall had better performance in noise than the OAD group. The difference was actually small. It was only 1.1 dB. However, this was statistically significant. No significant differences were found between groups for pure tone thresholds. A significant 1.1 dB difference was found between groups for hint performance. 1.1 dB corresponds to an 11% change in intelligibility. Recall that for every dB change in hint threshold, that represents a 10% change in word recognition ability, or you could say a 10% change in intelligibility. The results are very similar to those of Middleweird in 1990, who found a 1 dB difference between Dutch, OAD, and control groups. Of course, in the Middleweird study, they did not call them OAD subjects. Next, when I was at the VA in Long Beach, I met a lot of veterans. I was working in the Department of Audiology, and I met a lot of young veterans who would tell me during the case history that they really struggled to hear speech in background noise, like a noisy restaurant. And so I tested their hearing, and with the tools that I had at the time, there were no speech recognition and noise tests at the time at the VA in Long Beach at that time. And so I was testing their hearing. They had normal audiograms, and I was trained to tell them, well, sir or ma'am, you have normal pure tone thresholds, therefore you have normal hearing. And they'd look at me and they'd say, this is normal? Are you sure this is normal hearing? Because they know about their struggles to hear speech and background noise. But all I had was the audiogram, tympanograms, acoustic reflex thresholds. I looked at it. I looked through I looked inside the ear. We did speech reception thresholds, and we did word recognition scores. Everything checked out. However, what was their complaint? Their complaint was that they were struggling to recognize speech in noise. But all our test results were normal, so I said, well, you know, your hearing is normal. You actually don't have a difficulty. And again, they'd say, well, wait a minute, but I do have a difficulty. So things weren't making sense to me at the time. And my answer to them that they had, or my response to them regarding their normal hearing just wasn't, I could see that it wasn't a satisfactory answer for them. So I thought, you know what, maybe there is some early damage to the outer hair cells that is not being picked up by the audiogram or our standard speech tests. And if we did a hearing and noise test, maybe we would see a relationship between outer hair cell function and hearing and noise ability. So recall that the outer hair cells contract and expand in response to sound, at least when they're healthy, and they add motion to the basilar membrane. This is called the cochlear amplifier. This is what allows us to hear very low-level sounds. And this ability is decreased when a person is exposed to high levels of noise, especially in the region from 3 to 6,000 hertz. Generally, we see a notch on the audiogram, and that's called a noise-induced hearing loss, or we also call that notch the noise notch. So I thought, well, maybe there's a relationship between how these outer hair cells function and speech recognition and noise ability. Here are our data. On the y-axis, you see the average high-frequency DPOAE, distortion product otoacoustic emission, amplitude in dB/SPL. So I just averaged the DPOAE amplitudes from 3.2 to 5.7 thousand hertz. And so that was our measure of outer hair cell function. So a higher number, a more positive number, represents higher functioning outer hair cells. These are lower functioning outer hair cells with any scores down here. This is the HINT composite score. -9 is a very good score. -3 is not a very good score. And you can see what looks like this relationship. It's actually a statistically significant linear relationship. It's an inverse relationship of an R that equals about -0.6, and it is statistically significant. So the better functioning the outer hair cells, the better the HINT score. The poorer functioning the outer hair cells, the poorer the HINT score. And we also had a few outliers who had the poorest HINT scores, but their OAEs were were functioning relatively well. So it appears that the site of lesion was not in the cochlea. Most likely it might have been in the 8th nerve, it might have been in the brainstem auditory pathways, or it could have been in the brain. So the data indicate a relationship between outer hair cell function and hearing and noise ability. This is consistent with the results of Zhao and Steffens in 2006, who found differences in OAE amplitudes between control and OAD groups. Actually, they didn't call them, didn't call their OAD group an OAD group. They called it a King-Kopetsky syndrome group, which is really basically the same thing. Normal audiograms, but the self-report of difficulty recognizing speech and noise. Now here is a KKS patient with a presumably central component. There was a lady who was seen at the house clinic years ago. The audiologist down there called me up and said, "Hey, we have a lady here with a normal audiogram and severe speech recognition and noise difficulties. Would you like to run her through your test protocol?" I said, "Yeah, I'd love to do that." So I ran downstairs, brought my informed consent form, and I talked to her, and I said, so your pure tone thresholds are within normal limits. And then I measured her speech recognition and noise ability with the hint, and look at her score. It's right around a -4 dB SNR. Very, very poor score. And I said, and then I talked to the audiologist. The audiologist said that her ABR was within normal limits. So we're going to presume that the neural pathways from the 8th nerve through the brainstem was within normal limits. I looked at the DPOAEs, fairly robust DPOAEs, implying relatively high-functioning outer hair cells. And then I asked her, I said, when have you always noticed speech recognition and noise difficulties? And she said, no, it didn't occur until after my surgery. And I said, what surgery did you have? And she said she had a temporal lobectomy. So this shows us that presumably, we know that she had a lesion in the cortex, and her hearing and noise difficulty doesn't seem to be related to the function of the cochlea because the outer hair cells were normal. Doesn't appear to be related to the function of the 8th nerve or the brainstem pathways because those were relatively normal. I mean, according to the audiologist, the ABR was normal. So it appears that this patient actually has a legitimate central auditory processing disorder. Okay, can we use the classification of hearing based on the audiogram to predict speech recognition and noise ability? In other words, can we use the audiogram to predict how well a person will understand speech and noise? Now, we know we can't use a normal audiogram to say that, yes, they're going to have difficulties, or no, they're not going to have difficulties. But what about other audiograms? What about like a severe high-frequency hearing loss? Well, those people have speech recognition and noise difficulties. In other words, let's ask it this way. Which hearing group will have the greatest difficulty understanding speech and noise? A group of people with normal pure tone thresholds or a group of people with severe high-frequency hearing loss? Which group will have greater difficulty? So we looked at a very large group of subjects. It was actually 278 research subjects. And we collected audiometric and hint data from 4 test sites: the House Ear Institute, the House Ear Clinic in Los Angeles, the University of California, San Francisco Medical Center in their audiology clinic, and San Diego State University. And then the data were combined into high-frequency hearing loss groups. So we had a group with normal audiograms and then groups with various degrees of high-frequency hearing loss. And an effort was made to create pure tone threshold groups that were somewhat symmetrical. So the pure tone thresholds, when you look at the left ear versus the right ear, the hearing losses were somewhat symmetrical and homogeneous. And the way we did that was we said, okay, we're going to omit from the analysis anybody who has an audiogram where the low frequency thresholds are greater than 25 dB. We're going to throw them out. Anybody who had a no response for any frequency, we threw them out. Anybody who had an asymmetry between the pure tone average for the high frequencies, where the difference between pure tone averages was greater than, or were greater than 15 dB between ears, we threw them out. And then for each pure tone threshold groups, all the audiograms were omitted that had high frequency pure tone averages greater than ±2 standard deviations. We tossed them out too. Okay, we removed 63 subjects, or roughly 25% from the study. The pure tone threshold classification scheme created by Goodman and modified by Clark was used on the data for the remaining 215 subjects. The age range was from 17 to 59 years. The mean age was 33 years. Bilateral pure tone averages were determined for various configurations for each subject, and the standard hint protocol was used. Basically, these are our groups. Everybody had normal low frequency pure tone thresholds, and they had either a normal high frequency thresholds, 15 dB or better, or a slight, what we're calling a slight loss, 20 to 25 dB, or a mild loss in the highs, a moderate loss in the highs, a severe loss in the highs, and a profound loss in the highs. Recall our question is, which group, one of the questions, which group will hear better in noise? The group with normal pure tone thresholds or the group with a severe high frequency hearing loss? So the hint thresholds were compared to pure tone averages. We looked at differences across groups, but we also looked at correlations. So we were looking at the correlation between the pure tone average and hearing and noise ability. And don't forget, from your statistics class, we're looking at a linear association between variables. So we're going to test for that. Between the x variable and the y variable, the main result of a correlation is called the correlation coefficient, or the R, with a range from -1 to +1. And R closer to +1 or -1 indicates that the two variables are linearly related. And R close to 0 indicates that there is no linear relationship between variables. And here's a snapshot. So if you had an R equals 1, that means that there's a 1-to-1 relationship between the x variable and the y variable, and then all the data would line up in this nice straight line. If you had a correlation coefficient of R equals 1. Now, if it's 0.8, you see some spread in the data. 0.6, you see more spread. 0.4, is there a relationship between the x variable and the y variable? Well, not so much. A 0.2, not really. What about a 0? No, it just looks like a shotgun blast. We don't see a relationship between the x and y variables. We also have negative correlations, so when R equals -0.2, -0.4, -0.6, -0.8, and then a -1. So that's a review with correlation coefficients. And now back to our data. So here's the relationship between hint in quiet thresholds and the bilateral pure tone average for 500, 1000, and 2000 hertz. So can we predict from the audiogram how well a person will recognize sentences in quiet? And the answer is, well, yes, to some degree we can, because we have a relatively nice strong correlation coefficient where R is close to 0.8. So the better the pure tone average, or the better the pure tone thresholds, the better the hearing and quiet performance. And the poorer the pure tone average, the poorer the ability to recognize speech in quiet. And 64% of the variance for the hint and quiet performance is related to the variance for the bilateral pure tone average. So there's that graph again, right there. We looked at bilateral pure tone average versus the hint and quiet threshold, and you see this nice high correlation. It's significant, of close to R equals 0.8. But look, we looked at this across all these hearing and noise conditions and the quiet condition, and for different configurations of bilateral pure tone average. Sometimes we added in 6,000 hertz. So this is a bilateral pure tone average for the higher frequencies. This is a bilateral pure tone average from 500 to 6,000 hertz. This is the bilateral pure tone average for 500 through 2,000 hertz. The pure tone average for 500, 1,000, and 2,000 hertz is generally used in the clinic in audiology, though it's usually used for presented for each ear individually, not bilaterally. And look at the relationship between the quiet threshold and the bilateral pure tone average. Not as strong, a very strong relationship, but look at it for the relationship between the noise threshold and the bilateral pure tone average. There's no relationship there. Nothing is significant. As a matter of fact, let me go back. When you look at this, what you see is that there's no significant correlation for any of the noise conditions and the bilateral pure tone average from 500 to 2,000 hertz. However, when we add 6,000, we do see some significant relationships, but the R values are very low, meaning that the relationship is relatively weak, and it would be very difficult to predict speech recognition and noise ability from the bilateral pure tone average for these conditions. Okay, here's the high frequency pure tone hearing loss groups versus and their hint performances. So we're looking at the maximum pure tone threshold between ears, just to separate the groups out, just for illustration. And the hint composite score, recall that a -9 is a good score, a -1 is a very poor score, and we're looking at the hint composite scores for 215 subjects. Here are our subjects with normal pure tone thresholds, 15 dB or better, and here's our group with the slight loss. So we would expect to see that the poorer the hearing loss, so this represents a greater hearing loss, this represents normal pure tone thresholds, we would expect to see some sort of relationship like this, whereas we get, as the subjects have poorer and poorer high-frequency hearing, you'd expect to see poorer and poorer speech recognition and noise ability. Here's a group with a mild loss, rather, a moderate loss, and a severe loss. Look at that. Look at that range in performance. So it appears that the scatter, or the variability of the scores for a group with a severe high-frequency hearing loss scatters just as much as a group for a group of individuals with normal pure tone thresholds, 15 dB or better. And then here's our profound group. We only had 4 people there. So the question is, can we use the audiogram to predict how well a person will recognize speech and noise? And for the most part, the answer is no. Here's a couple percentiles. So this is the 5th percentile for individuals with normal audiograms. So on those case studies, when we looked at the 5th percentile, that defines the bottom edge of normal limits. So this is speech recognition and noise and ability within normal limits. This is below normal limits. And this red line represents, it's actually the 50th percentile for our distribution, but it's also the 5th percentile for a group of people, a group of subjects with normal audiograms who report that they do not have speech recognition and noise difficulties. And that's from our previous study. So again, a group of subjects with normal audiograms, this is the 5th percentile for that distribution, for their hint scores. So is it possible to have a hint score where it's within normal limits and yet the patient will still report some hearing and noise difficulty? The answer is yes. How did we norm the hint? We normed the hint on individuals with normal audiograms. We did not ask anybody if they had difficulty recognizing speech and noise. We normed this test the way people all over throughout the literature have normed their test. We based it on the audiogram, and we didn't discover this issue about people with, or rather subjects with normal audiograms who had very poor speech recognition and noise ability. We didn't. I mean, that wasn't even on our radars at the time. Okay. Now, even though it says the study is 2012, we actually worked on this several years ago. So that's why I'm saying that, in case you got confused on that point. Plomp and Mimpin described 2 components of hearing disability, attenuation and distortion. Attenuation refers to pure tone sensitivity. Distortion refers to the ability to recognize speech and noise. So here is our graph. Now I've illustrated for you with this red line. This is a group of folks from a previous study that reported no difficulty hearing speech and noise. So this is the 5th percentile through the 95th percentile for the distribution of hint data for those subjects. Now the blue group represents a group of subjects with normal audiograms who reported that they have difficulty hearing speech and noise, and this is again the 95th percentile through the 5th percentile for those subjects. So you can see how everything compares in this regard. Now anybody who scores below the 50th percentile, we're going to say that they have some sort of speech recognition and noise ability. So it's below average. Below average. And again, it's below what's normal for a group of subjects who report no difficulty hearing speech and noise. So if we norm the hint on individuals with normal audiograms who reported no difficulty recognizing speech and noise, that would be our 5th percentile. But we norm the hint on individuals who had normal audiograms. We didn't ask them if they could hear well, if they could understand speech and noise well. So I think you get the picture. So this represents distortion according to Plomp. All right, some sort of speech recognition and noise difficulty. And then this could also be called a signal-to-noise ratio loss. Mead-Killian has talked about a signal-to-noise ratio loss, and that's relative to the 50th percentile. So this would be representative of a 1 dB signal-to-noise ratio loss, a 2 dB signal-to-noise ratio loss, etc. And then this blue shaded region would represent somebody with an audibility loss, or as Plomp calls it, attenuation. Any scores poorer than 25 dB HL would be considered some sort of loss. And now we have 4 zones. We have the audibility loss only group, so no speech recognition and noise difficulty, but they do have some audibility loss. We have a distortion only group, so meaning that they only have a speech recognition and noise difficulty. Their audibility is fine because their audiograms are normal. And then we have an audibility loss and distortion group, and that's for, so they have difficulty understanding speech and noise, and then they have an audibility loss represented by the audiogram. Now what about this 4th zone over here, this last zone? What do you think we should call those individuals? Right, we're going to call those the normal group, the group with normal hearing. So the hearing is normal, and we're defining it with the audiogram, and we're defining it with the hearing and noise test. So that they have normal speech recognition and noise ability, and they have normal pure tone thresholds. And then just to give you a reference point, this subject with a -4 dB SNR composite score, I met a young lady who had that score. Her thresholds were 15 dB or better. She said that she has great difficulty recognizing speech and noise, and she routinely uses her son as her hearing aid. What did they say? She said that she routinely uses closed captioning on the television. And she said if there's noise and speech in the room, the noise always wins. So this gives you an idea of what a -4 dB signal-to-noise ratio means. This is a lady who walked out of her cousin's wedding because she was miserable, because she couldn't carry on any conversations in the noisy wedding banquet. So this is a very, very significant speech recognition and noise difficulty. And that would be equivalent, according to this SNR loss scale, of 2.3 dB. Okay, and that's our first lecture on research using the hearing and noise test.